Screen is visible, right? Please confirm.
Yes, ma'am.
So I'll continue. SVM. We have these are the topics remaining for the SVM, soft margin SVM, nonlinear SVM, in that kernel trick and SVM kernel, and the difference comparison between SVM and logistic regression. It's a mathematical comparison. And then we have another small topic remaining, FactML. So that's the agenda. A quick recap for the linear SVM, what we did. It is also known as linear SVM, also known as a maximum margin classifier. So we get a separating hyperplane where the border points of both the classes are as far as possible. And mathematically, we have to train the model to achieve that decision boundary. And the objective function is a quadratic objective function. So we have seen the objective function, how we are deriving the objective function, and how are we solving objective function to get the optimized values of the parameters. For that, we are using Lagrangian function using KKT condition. Now, our hypothesis function is all in the form of Lagrangian function. That's a dual function we get, and we have only one variable, which is a Lagrangian multiplier, and there are certain constraints. So now this linear SVM, sometimes also known as hard margin SVM, it assumes that there are no data points between the margins, and based on that assumption, we have come to the objective function of SVM. But that's not the real world scenario. The first situation, what first scenario is that where the training set itself is noisy. So as you can see, blue dots and the white dots, we have certain noisy points which are on the other side of the class. This is a situation where we have only few data points which are not at the correct side of the decision boundary, and they are noisy points. It's not like the data set is more or less linear, but with addition to this noisy points. So that we can solve using something called a soft margin SVM. So you can see over here, we have a margin, and in soft margin allows certain misclassification happening. That means soft margin allows certain data points can exist between the margins, could be on the wrong side of the decision boundary as well. So you can say these are the two margins, circle class and the square class, and we have certain data points within the margin. In this example, this is a data point which is on the opposite side of the decision boundary within the margin. Or this also soft margin is also applicable when data points could be on the correct side of the margin, but still they are within the margin. And those are the points which are very difficult to classify because they are very near to the decision boundary. They are inside the margin. That means they are very near to the decision boundary. For to solve such problem, we are introducing a variable known as a slack variable, which can be added to allow misclassification of a difficult or a noisy example. So what do? We can add this slack variable for every data point xi. Along with every data point, we'll have this slack variable. And intuitively, what is a slack variable? Though it is not in a very mathematical sense, but intuitively, it is a distance of a point from the corresponding class's margin. So say, for example, this point, which I've just put a box around it, it is the white point, and you can see which is on the opposite side of the margin. So it's a noisy point. It's on the wrong side of the margin. It's within the blue class data points. Then we can introduce a slack variable where, it is there with every data point, but intuitively, we can say that the distance between the point and the margin, the correct margin. So this distance, as you see here in the diagram, this distance is nothing but the slack variable, the value of the slack variable. Here we are not talking about a Euclidean distance, but we will use a different distance function. I will explain in a while. But intuitively, you can say that if any data point, like here, the blue data point, which is on the wrong side of a decision boundary, then we can measure its distance from its own class boundary. So this is the correct blue class boundary. Sorry, it's a margin. It's a correct blue class margin. And this is a point which is on the other side of a decision boundary. The distance between this two is nothing but a slack variable. Likewise, for every data point, we'll have that distance. So here you can see.
Madam, every data point or only misclassified point, madam?
No, there will be slack variable is there with every data point. Now, the way the slack variable function is defined, any data points which are on the margin or on the correct side of the margin, its value would be 0. So you can see here two red support vectors, the slack variable value will be 0. Even all of these points which are on the correct side, even the blue side also, all of those points slack variable value would be 0. Slack variable can have only 0 or a positive value if any data points which are within the margin. So you can say over here, you can see the red one is within the margin, but it is, you have to mute your mic, but it is on the correct side of the decision boundary. It's on the red side. For that, the slack variable value would be any value between 0 and 1. And any points which are away from the margin, which are on the wrong side of a decision boundary. Say, for example, here, this red point. You can see it is on the blue side of the decision boundary. It's on the wrong side of a decision boundary. Then for those points, like variable value would be greater than 1. So this value will tell us whether that point is on the correct side of a margin or a wrong side of a margin. If the value of slack variable is between 0 and 1, then those points are within the margin, but on the correct side of the decision boundary, like the point number 1. And the point number 2, its slack variable value would be greater than 1, as it is on the other side of the decision boundary. So this is how the notion of slack variable have been introduced. We have to modify our objective function. This part is the original objective function, half of a norm of w square. This objective function will ensure that we are getting a maximum margin classification. That's what we saw in the last class. Now we are introduced the penalty in the form of a slack variable. So we are going to introduce a penalty for a misclassified points in the form of the slack variable. As you can see, the slack variable is there for all the data samples, but for the correctly classified points and they are outside the margin, the value would be 0. For the data points which are within the margin, but on the correct side of the margin, will have some value, and the data points which are on the wrong side of the margin will also have some value of slack variable. So only I can say that, along with that, we are introducing one constant. We can call this as a regularization constant or regularization parameter, which is also known as a misclassification constant, which will control how much misclassification can be allowed. So, okay, before that, now we have to find out what is this slack variable equation. The notion is clear, the intuition is clear. The slack variable function is nothing but a function which is used for something called a hinge loss. And it is this simple function. This is nothing but a hinge loss or a slack variable function. This way we can identify the values of the slack variable. Maximum of 0, 1 minus y of I. That means the actual value of a classification multiplied by theta transpose xi. What is this theta transpose xi?
predicted value.
Predicted value. We take for a class, we take the sign of a predicted value. But yeah, this is a function that we use inside the hypothesis function. 1 minus this value will give you the value of the slack variable. The intuition is that it's nothing but a distance of a point from its margin. Now let's say intuitively, what is the effect of this slack variable? Say when our true class is positive and our theta transpose x, and we take a sign of theta transpose x. So which is also predicted is also positive 1. If that is the case, what will this equation will be reduced to? Both y is equal to 1 and y hat is also equal to 1. Y hat is nothing but say theta transpose x.
Zero.
0.
Oh.
It
Yeah,
will be
1
0.
minus 1, right? Yeah.
Yeah. So max of 0 by 0, max of 0 comma 0, so it's 0. So you can say, or any value of theta transpose x is greater than 1. We take a sign of theta transpose x, okay? Don't take a literal value of theta transpose x. The loss is going to be 0. So on x-axis is theta transpose x and y-axis is a value of the slack variable, which is going to be 0. Now say when our y hat is 0, the predicted value is 0 and the actual value is still positive 1. So in that case, what will be the value of slack variable? Yes.
1.
1.
It's max of 0 comma
1 minus 0.
1 minus 0. So that
1 minus 0.
So it will be 1, correct? So at this point, when the theta transpose x is 0, you can say the slack variable value is having some value, which is 1. You can say, so as we keep on changing the values of y hat, in a classification anyway, we are interested 0 and 1, but here inside it is not y hat. It is theta transpose x. So it could be some minus value, minus 0.5, and we take a sign. So for those values, we will get some value of the slack variable. As we go near to the actual truth, ground truth, the slack variable value will become 0. The same argument you can see on for the negative class. When the ground truth, the class is -1, and then plug in the values in this equation, take a different values of theta transpose x. When ground truth is -1 and theta transpose x is also -1, -1 into -1 will be +1. I mean, okay, this is -1 and 1 minus 1, 0. So we'll have the loss of 0. That means slack variable value would be 0. Hinge loss is also used in a lot of other places, but here the hinge loss is used to identify the value of to calculate the value of the slack variable. Now, the effect of C. This is our j theta. This is our modified cost function. The first term, what we try to do with the first term, it's a minimization term, and we get a minimum value of the first term will actually result into what? Can I say it will result into the maximum value of the margin? It will maximize the margin if the first term, if we are able to minimize. Correct? Yes. This is our objective function of SVM, linear SVM. It's a minimization function, half of norm of W square. So when we minimize this function, we are ensuring we are maximizing the margin. Correct? That's what we did in the last class.
Yeah, yes.
Now say, what is the effect of this regularization parameter? Before that, what happens whenever margin is maximizing? We may get certain data points within the margin. There's always possibility because we are going with a soft margin approach where we are allowing this by introduction of slack variable. So maximum margin ensure maximum margin results into the situation where we have certain points, as you can see here, inside the margin. Maybe on the correct decision side, correct decision boundary, on the correct side of a decision boundary, maybe some of them could be on the wrong side of a decision boundary. What is the advantage of having this kind of a situation by maximizing the margin and allowing some misclassification to happen? Here, what is happening? This is a point which is misclassified. We have a circle and we have the cross here. Rest of the points could be, they are on the correct side of the decision boundary, but on the within the margin. But still, they will be classified correctly. But the point which I have just put a box around, it is on the wrong side of the decision boundary. Because we have maximized the margin, we get such points within the margin. That means these are the points which will be misclassified. That means when we increase the margin, when we increase the width of the margin, we are allowing some misclassification. Some misclassification is allowed, but we want a large margin. So in this scenario, classification mistakes are given less importance. During the training, we are allowing some misclassification to happen. So tell me, why is this scenario suitable and what case this scenario is suitable? Okay, let's see the other right hand side diagram. Then I'll come to the value of C. The other side of a diagram, you see the margin is very narrow. Do you see any points within the margin on the right hand side? We don't have any points here. That means we are identifying a margin such that no misclassification is allowed. So in this case, we are avoiding the misclassification at the expense of keeping the margin small. So when we maximize the margin, it allows the misclassification, but we do not allow the misclassification and then find the margin accordingly, that we don't want any misclassification to happen. So which of this scenario gives a better generalization performance? Left one or the right one? The left one.
Left one.
Correct. Okay, now there's always a trade-off. How much misclassification we want to allow? If we allow a lot of misclassification, then training error will be very low. Our model will end up with high bias. So always we have a trade-off between bias and variance. But yes, on the left scenario, it will help in reduce the variance, reduce the overfitting. But the right scenario will have very low bias, but may not give a good generalization performance, may result into overfitting. Now, how do we ensure this kind of margins? By controlling this parameter C. So if the value of C in the equation is small, we end up in getting this kind of left side margin. And if we have a higher value of C, which is a constant and it's a hyperparameter, then we'll end up the right side margin, which is shown on the right side. So when we look at this equation, what role the C plays here? Suppose when C is very large, and on the right hand side, we can have some value, max of 0 or some other value. Some value multiplied by a very large value of C, say 100. That means the second term is more dominating compared to the first term, and the first term is maximizing the margin. But if the second term is more dominating, then we cannot reduce the first term, like in the minimization objective, that will not result the maximal margin. So when the C value is of high C value will not result into maximal margin. The other way, when the C value is very small, say less than 1. So any value which is less than 1 and you multiply it by anything, the second entire term will be very small. So in the entire minimization objective, the effect of the first term will be more compared to the second term, which anyway is very small number, due to this regularization constant C, which we have chosen as a very small number, less than 1. So when the first term is more prominent, when we minimize this entire equation, we are more of minimizing the first term, which actually controls the margin width. So indirectly what we are doing, we are ensuring that we are maximizing the margin. So that's the effect of C. It's a hyperparameter regularization constant in case of soft margin SVM. So now we have, okay, this is a summary with the soft margin. Now our optimization problem doesn't have only the first term, but we have introduced the slack variable with a regularization constant, a regularization parameter, hyperparameter, which allows certain misclassification within the, and also allows certain points within the margin. So our constraint equation will also change. The original constraint equation was only this much. And we have introduced now a slack variable. So it's minus slack variable. So slack variables will have only values for those points which are within the margin. So when we do SVM training, we are giving input X and Y. Now we have this regularization constant C. This is not exactly same as the lambda for L1 and L2 regularization, but later I'll show there's a relationship between this C and the lambda, which you are aware of L1 and L2 regularization parameter. This C is a different, slightly different than that. The output will be what? We'll get the alphas, which are nothing but the multipliers, Lagrangian multipliers, and the Bayes value. And here hyperparameter is C. And then once we train the model, which try to optimize this objective function, we can use it for inference using our hypothesis function, which is a sine function of W transpose X. And we can, rather than W, we can use it as alpha I yi xi. This is what we have seen in the last class. Alpha I yi xi. This is the soft margin SVM. Any doubts here? Okay. So the next is nonlinear SVM, where we have our data set inherently nonlinear, not because of noise, but the way data is generated, it has got a nonlinear relationship. Take a simple example here. The first case is a linearly separable data or non-linearly separable data?
Linearly.
Linearly separable data.
Then second here,
Non-linear.
No.
can we pass a linear boundary? Can we divide the data set using linear decision boundary in the second case?
No.
No.
This is a one-dimensional data. Just one feature. If we
Yeah.
introduce another feature and we make this one-dimensional data as a two-dimensional data, so you can think about we have a one thread, okay, and on the thread we have certain knots which are all mixed knots, red knots and the blue knots. Now in order to separate this red and blue knots, you can bend the thread. So when we bend the thread, this way we are bending the thread. So when we bend the thread, we get a two-dimensional figure U. The single thread on a horizontal line is a one single line. It's a single dimensional figure. But when we bend the thread, we get a two-dimensional figure. So the same applies here. We have bent this original dimensional data, and by bending, now you see that we can pass a linear decision boundary, which can differentiate clearly between red class and the blue class. This is the intuition of nonlinear SVM. Okay, let's see some more example here. Left side is a two-dimensional data. We have two features. And you can see decision boundary is a circle. It's not a linear, it's a non-linear decision boundary. We transform this, which is a two-dimensional data set, into some high-dimensional data set. In this example, we are transforming it into some high-dimensional data set. And now we get a plane with which you can say that we are able to get the linear decision hyperplane which can divide blue class and red class. Say this another example. We have this decision boundary, which is oval in shape, hyperbola. And then the two-dimensional space, we have two features. We can introduce few more features in high dimension. When I say transforming a data set into high dimensional, that means we are introducing more features by a different combination of already given features. And now we have gone to some high dimensional, say three-dimensional. So we have introduced third feature. And now when we pull the red part apart, we get this kind of a cone shaped figure, a three-dimensional figure, where you can see the red part and the green part are separated linearly with a linear hyperplane, which is a three-dimensional linear hyperplane. This is the intuition behind nonlinear SVM. Mathematically, we can write this. The original feature space is being transformed to the high dimensional feature space. And then the original data set, which was non-linear in a feature space, becomes linear in a transformed feature space. I can say high dimensional transformed feature space. For ease of drawing this diagram, we are showing 2 and 3 dimensional example. Not necessarily from 2 dimensional you move to 3 dimensional, then you get a linear boundary. Maybe from 2 dimensional to say 20 dimensional. But in that dimension, we get a linear boundary because 20 dimension cannot be visualized. So only 1 dimension, 2 dimension, and 3 dimensional figures you will find everywhere to understand this non-linear SVM. Okay, so this is some concrete example. The top figure is 2-dimensional data set. R square stands, it says that 2-dimensional real numbers. Please mute yourself. There's a background noise.
So why won't it come to your friend? So why would you hit him? My game, I hit him and he hit.
Okay, so we have two features, X1 and X2, and we have handcrafted to these 3 features. One is X1 square, second feature is X2 square, and the third feature is root 2 X1 X2. From 2-dimensional input space, we are going into the 3-dimensional feature space. So that's a transformation is happening from 2-dimensional to 3-dimensional. And then we have a standard with every feature, we have the corresponding weight. And the hypothesis function of SVM is a sine function, W1 X1 square, W2 X2 square, W3 into this, plus bias term. Now with this function, so you can say the decision boundary was hyperbola. In moving to 3-dimension, we get a decision boundary which is linear hyperplane. Again, this is a 3-dimensional, okay, just shown with the help of 2-dimensional, just for illustrative purpose. So it says that in nonlinear SVM, rather than running SVM on the input space, the original feature, we will run on the feature space. That means we are transforming and generating more features. And then increasing the dimensionality of the input. And that is how we get a linear boundary. And then once we ensure we get a linear boundary, we can use all the hypotheses and all the training what we learned last class can be used to use this to train the nonlinear SVM problem. Now you have done this before, this kind of transformation. Do you remember that? Like we have got a X, we transform into, yeah, so it's a linear basis function. Quite related, this concept is quite related to that. Okay, so this is, we have input space. We perform some kind of nonlinear transformation. We go to the higher dimensional feature space where we get the linear decision boundary. Now this higher dimension is actually very, very high dimension. And each individual feature has to be transform to the new dimension. Now, suppose, for example, from 2-dimensional, if we are going into 20-dimensional space, that means we have to first create this 20 features and then perform this theta transpose 5 of x. Each of the feature, or let me write this. Okay, there is a confusion in writing. Theta phi looks similar, so let's have W transpose 5 of x. This is the feature transformation. So original is W transpose x. Rather than that, I'm doing this. But imagine we have 20 features, so we have to do a lot of computation. We have to generate this 20 features. That means individually we have to transform to the higher feature space, then perform the dot product. This is a dot product between W and this transformed feature space of high dimension. This is computationally very expensive. That initially first we create those many features and then perform the dot product. Our hypothesis function is a sign of a dot product, sign function, then dot product function. So the idea remains the same, but something called a kernel trick, which is the heart of this nonlinear SVM, comes to our rescue. That we don't want actually to create so many 20 features, like moving from 2-dimensional to 20-dimensional. This is just an example. We don't want to create so many features. We don't want to transform into a feature space, but get the same effect. That is performing a dot product into the feature space, high dimensional space. For that, we use the SVM kernels, and the kernel function is used. So if you read this, they only calculate the relationship between every pair of points, the original points, the original data points, as if they are in some high dimensional. Using the kernel function, they actually do not do any transformation. So mathematically, those functions are such that if you see, this is a kernel function which mimic the behavior of as if we are performing a dot product in some higher dimensional space. So trick is calculate this high dimensional relationship, which is nothing but a dot products, without actually transforming the data to higher dimension. There are many such mathematical function available like linear, and depending upon what mathematical function we are using, we can call it linear kernel, non-linear kernel, different polynomial kernel, sigmoid kernel, etc. There are a huge mathematical function can be used, set of functions can be used as a kernel function. So how our hypothesis function changes now? We have theta transpose x, which is theta 0 plus this is our alpha I. This is nothing but W. Okay, theta transpose x. We have separated the bias term here. Okay, and then W is nothing but what? Summation of alpha I yi into xi. So this way we are writing our hypothesis function where we have separated the bias term and we are writing in the form of alphas, which are nothing but the Lagrangian multiplier. And now you see we get this dot product. We are talking about this dot product here now. X transpose xi, rather than this dot product, which is of very high dimension, what we will do, we will write the kernel function, which is x transpose x, which emulates this dot product, which is actually written by z transpose z of I. Z is nothing but this kernel function. So z is 5 of x, and these all are the support vectors. In this equation, we know this. X of I are the support vectors, and x where x transpose is mentioned, it is your test data point. So between the test data point and all the support vectors, we'll apply the kernel function. The kernel function could be very simple, linear kernel function. This is nothing but our original SVM problem. For a linear SVM, we can say that the kernel function is simple dot product between the support vectors and the test points. We can have polynomial kernel. We can have a Gaussian kernel with this equation. We can have a sigmoid kernel with this equation like that. Likewise, any function, there are certain rules. It's not like any function can be used as a kernel function. There are certain conditions, mathematical condition. If it gets satisfied, those functions can be used as the kernel function. I'll give you those conditions. First, let's see how this kernel trick ensures that we are actually performing a dot product into the high dimensional space. See, original we have two vectors A and B, just two features A and B. Okay, I mean that we have two vectors A having features A1 and A2, another vector having features B1 and B2. These are our two features. You can say A and B. Now we want to perform a nonlinear SVM. Let's say we are transforming each of the features individually first. So this is 5 of A, this is 5 of B using some transformation function. And from two dimensions, two features, we have created three features. A1 square, A2 square, and root of 2 A1 and A2. Similarly, we have also created a three from the two-dimensional vector. We have created a three features, B1 square, B1, B2, and B2 square. And then we'll perform the dot product. You can just use a simple vector to vector dot product formula. This is what you will get the answer between these two. Now further simplify this mathematically. This is nothing but A1 B1 plus A2 B2 the whole square. Now A1 B1 plus A2 B2 the whole square is what? If I write this A1 A2 and we do the dot product between B1 and B2, vector vector multiplication, what will be answer for this? A1 into B1 plus A2 into B2, A2 into B2. So this inside is nothing but A1 A2 B1 B2 dot product. So this is nothing but A1 into A1, I mean A and B dot product, and square we are keeping it as it is. So we are squaring this. A transpose B is nothing but I can say the dot product between A and B, and we are taking the square of that dot product. Now what is the similarity between these two? We have come with the left equation which perform the dot product in a high dimensional feature space, but we can reduce it to something called perform the dot product in the original input space and square it. So this becomes our kernel function. Take another example. We have two vectors x and y having three different dimensions, and we are going to we are interested into this two dot product, like here. This two dot product, x transpose into x of I. X of i's are various support vectors, x1, x2, x3, and so on. Now our original data is into three-dimensional space. x1, x2, x3, y1, y2, y3. We have two different data points. One is a support vector, one is a normal point. We are transforming them into the high dimension. So first we'll transform the x point, then we'll transform the data point y into high dimension. See, this is a way we are defining 9-dimension, 3-dimensional data converted into 9-dimensional feature space. So you can say take a x1 of x1 square, x1 x2, x1 x3, x2 x1, x2 square, and so on. This way we are generating new features. Then perform the dot product between these two. You can perform this dot product. This is one vector and this is another vector. It will be reduced to this equation. Now say we use this kernel function, x transpose y the whole square, x1, y1, x2, y2, x3, y3 the whole square, because each of this x and y, they are three-dimensional vector. And then when we solve for this square, it will be reduced to this function. That means this kernel function x transpose y the whole square is equivalent to performing the dot product in the higher feature space. So what is the advantage? This is very simple to compute. Original x and y, perform a dot product and square it, which will give a similar result like this one, where we are individually transforming each of a data point into the higher dimension. Like here, 3-dimensional data is being transformed to 9-dimensional data, and then performing dot product. So when you perform a dot product of these two vectors, our number of computation required will be very high. X square, x1, y square into x2, y1 square, and so on. And in reality, this high dimensional space that we are talking about, it is really very high dimensional space. Then only we can say that in a high dimensional space, our data is linearly separated. Some another kernel example. It's a polynomial kernel. So we have to prove whether this kernel is equivalent to performing a dot product on the high dimensional space. Rather, we perform this mathematical operation in the original feature space, or each of a data point we transform to the high dimensional feature space and then perform the dot product. See, this is the kernel function. 1 plus xi transpose xj the whole square. This is what is the square function a plus b the whole square. We have done it. And we can divide this into 1 xi and 1 xj. So we can divide into terms of this is the xi feature, but it is a transformed xi feature. And this is the another feature which is transformed, another data point which is transformed into high dimension. So it is 1, 2, 3, 4-dimensional feature space from the original 2-dimensional feature space. This is very simple to because we have done this in a reverse way. You can say 1 is coming here both the places. Here we have to separate the I component and j component. So x1 I square is coming here, and this j component x1 j square is coming in the separate another vector. Likewise, we are separating I and j data points. That means I is our one data point, j is another data point, xi and xj is another data point, and we are performing a dot product in a higher dimensional space. So this is the kernel function. Now you can try perform a dot product between these two, 1 into 1 plus x1 I square plus x1 j square and so on. You will get exactly the function which is the kernel function. Likewise, you can say that you can try with a different mathematical function. This example is a very simple to understand. From 2-dimension, we are going to 3-dimension. How we are transforming individual feature A and B, individual features A1, A2 and B1, B2 into, oh, this is wrong. This is, I should write A1, A2. And we have B1, B2. Each of this we are transforming into high dimensional space, A1 square, A2 square, and root of 2, A1 into A2. And this calculation will tell you, make you understand that dot product in a high dimensional space, which is 3-dimension space, equivalent to the kernel function, square of a kernel function. It's a quadratic kernel in the original input space, which is just A and B vector, which has got A1, A2 and B1, B2, 2 components. Now, what could be the kernel function? There is something called Mercer's kernel. They can be used. The kernel function should be continuous. There should not be any discontinuity. And the kernel, when we convert into matrix, it should be symmetric function or symmetric matrix. So kernel xi xj is nothing but transformed 5xi 5xj, we can interchange xj and xi. So that's a symmetric function. Also, another condition for a legitimate kernel function, this kernel matrix should be positive semi-definite. It is from the linear algebra. What is the definition of positive semi-definite matrices? But yeah, very simplest form, X transpose kernel X. This should be greater than or equal to 0. This mathematical computation. Then you can say that kernel matrix is a positive semi-definite. So these are some just theory about what could be the kernel function. And we can create any kind of kernel functions like e raised to some distance function of support vector and the test vector. The distance function could be this, or we can put some condition on the distance function like this. Or we can have some constant, whether multiplied to the some other kernel, constant, some multiplied adding to the other kernel, or we can combine these two kernels in multiplicative way or addition way. Any legitimate kernel can be used to generate another legitimate kernel. So these are a lot of options for the SVM kernels. Now our optimization problem, your hypothesis function will change. In our dual problem, dual Lagrangian problem, we have a dot product, this xi xj. This equation is nothing but what we saw last time. It's a dual problem of Lagrangian, where xi xj dot product will be replaced by this kernel function. In short, you can also write this as the original xi xj will be replaced by the kernel function, which is nothing but dot product, performing a dot product in a high dimensional space. And here in this case, we have used the polynomial function of degree 4. This way, you can always replace the original xi transpose x by the kernel function involving this xi and xj. Okay, so theory is done. I'll show you this toy example. Should I go ahead with this toy example?
One question.
Huh.
How do we choose which kernel function to use?
It is more of a hyperparameter or more of a design problem. So a lot of researchers, they do with a different kernel function and report the results. It's purely experimental. But yeah, mathematically, there are so many valid kernel possible.
Okay, we need to choose any kernel function randomly and based on.
Yeah. And you can also go read the previous literatures, and people have reported which kernel function is good for what kind of a problem. But it is a random choice. It's a hyperparameter.
Okay.
Okay, now this is a example. We will use the same set of equation what has been done for the linear SVM last class after the transformation. Here I'm not using a kernel trick. Okay, this example is not using the kernel trick. This example is to demonstrate how we can use the linear SVM equations to separate the nonlinear data set after we transform them into high feature space. So that is the original idea, original concept. Kernel trick is the some kind of optimization, or you can say some trick we are using so that we don't have to do a lot of computation. So this problem is the original feature transformation problem. You can see we have this non-linear boundary separating blue points and the red points. And we have two features. It's a two-dimensional x1 and x2. The blue vectors are, these are the coordinates for the blue vector. You can say the first coordinate, this is 1 and 1. Then we have -1 and 1. And so on. So they are simple the coordinates of red and the blue vectors. This is a transformation function defined. So we are transforming x1 and x2 if this condition is satisfied. Otherwise, we are retaining x1 and x2 as it is. As I said, this is a toy example. This particular example will only transform the data point into two-dimensional to two-dimensional. Because we cannot easily visualize three-dimensional, this particular function we are using to understand the nonlinear SVM concept by performing two-dimensional to two-dimensional transformation. And for the transformation, these are the equation. First, some conditions are checked. If that gets satisfied, we individually transform each of the x1 and x2 vector. Otherwise, we retain them as it is. Okay, so let's see for the blue and the red class what happens. These are the blue class vector. There are five. How many points are there? Blue class. We have 4 data points for the blue class and 4 for the red class. These are the 4 coordinates of blue class vectors, and they're x1 and x2, both the coordinates. Check this condition. x1 square plus x2 square. So let's do it for 1. 1 square plus 1 square. What is the answer over here? It is root 2, which is definitely not equal to 2. This condition, which is greater than or equal to root 2 is definitely not greater than or equal to 2. Root 2 is less than 2. So this condition doesn't get satisfied. If this condition doesn't get satisfied, we are not transforming x1 and x2. We are retaining as it is. Same thing you can check for other 3 data points. This condition will not be, it's very clearly you can quick mental calculation you can do. When we do x1 square plus x2 square and the whole root, it won't be greater than or equal to 2. So blue class vectors are not transformed. As per this equation, they will stay as it is. Their coordinates will not change. Now, these are the red class vectors. There are 4 data points here. Red class vectors. We have taken those coordinates here. And now first we will check this condition. So I'm just checking for the first data point. This is x1, this is x2. 2 square plus 0 square, and we have square root should be greater than or equal to 2. So what is our answer for this? 2, which is definitely greater than or equal to 2. It is equal to 2. That means this condition is satisfied. We will transform this first point. So the first point is taken here, 2 and 0, and where x1 is 2 and x2 is 0. Plug in into these 2 equations. This is x1 minus x2 the whole square. So we'll perform this computation, and then bottom computation where this is x2 and this is x1 minus x2. x1 is 2, x2 is 0. And then we get answer is 8 and 10. So we can say that the original coordinate 2 and 0 is transformed to the coordinate 8 and 10. Still it is two-dimensional to two-dimensional transformation. As is a toy example, just for the understanding we are doing this. Similarly, all data points, this given condition is satisfied. So we will transform all of such data points, say 0 to transform to 10 8, minus to 0 transform to 12 10, 0 minus 2 transform to 10 and 12. You can say the original red data points now, those coordinates are changed. These coordinates are changed. And now we can clearly see which can be separated linearly. Okay, so just now we have to identify the support vector. We will not consider this original red, the original blue and the transformed red. Now, how many support vectors you can identify from this? Yes. How many support vectors? Huh?
3.
3. How many blues and how many reds?
2, 1, red 2.
Yes. So this is blue 1 is a support vector and this red 2 are the support vectors. So 3 support vectors we have identified. And what are the coordinates of support vectors? For S3 it is 1 and 1. S1 it is 8 and 10. And for S2 it is 10 and 8. Now we got the support vectors. How will we proceed this? Okay, first we have got these 3 support vectors coordinates. Introduce the coefficient of the bias, which is 1. So we have just rather than W0 plus W transpose X, we will incorporate W0 also here. So we have got the bias term 1 added. We got 3 support vectors. What it's the same. Now it will work similar way as a linear SVM, and you have to use the same equation. So what we will do from here on, we got 3 support vectors with their coordinates, their dimensionality values. What is the next step in SVM? Linear SVM, what did we find? The values of alphas, Lagrangian multiplier. This is our hypothesis function. We are using the same support vectors as the test vectors also. So alpha I, yi, xi transpose x. Here, rather than xi transpose x, we are using this si transpose s. This transformed vectors we are taking. You can say we will get 3 equations because we have 3 support vectors. And those, no, sorry, we get 3 equations because we have 3 test points. 3 support vectors are only my test points. So the first equation is for the first test point, which belongs to positive class. So we can say red is a positive class. Red is a positive class. And blue is a negative class data points. So we have 1 in the support vector. We have 1 negative class data point and 2 positive class data points and support vectors. This is for first support vector when it is used as a test point. So you can see S1 is a test point and it's a positive class. So its yi value is 1. This is yi. And these are the support vectors S1, S2, and S3 is a support vector. And similar way, perform this for each of the 3 points support vectors considered as a test point. So here these are the test point. These are the test point. And each of the 3 will be acting as the support vector as well. We'll get 3, substitute the values of S1. So that's what we have done. S1 is a transformed support vector S2 and S3. This coordinates, we got it from here. S1, S2, and S3 coordinates, we have got it. This is S1, S1. This is S2, S1. And finally, this is S3, S1. This equation is nothing but summation of the previous one. Alpha I, yi, Si transpose, Si. Plus B is not there because we have incorporated bias term inside. So this is yi. And here the negative sign is because of the yi, which is -1. Here it is -1. S1 vector, dot product between S1 and S1. The one S1 is acting as a support vector. The other S1 is acting as the test point. Now we are S2 and S1. So this S2 is a support vector. And this S1, which is anyway constant for that equation, is nothing but a test point. So now we are getting alpha 1, 3 simultaneous equation and 3 variables, which are alpha 1, alpha 2, alpha 3. we got this 3 equation here. You can perform the dot product. So let's say simple dot product. 1, 1, 1, 1, 1, 1. So what is the dot product of this two? Yes, 3. So you can say here it is 3 alpha 3. I've shown this simple calculation. This dot product is nothing but 3. Similarly, perform all of this dot product. We got 3 simultaneously linear equation in 3 variables. When we solve for this, you will get alpha 1, alpha 2 and alpha 3 values. There were certain corrections, so I have already done those correction. There was signed mistake. Whatever online document available, there is a sign mistake over here. So refer to, I have already changed this sign. Use pen and paper and make this linear SVM equations. Solve for alpha 1, alpha 2, alpha 3. So what is W is alpha 1, Y1, X1 plus alpha 2, Y2, X2 plus alpha 3, Y3, X3. Here we have got X1 is nothing but S1. This is S2. This is S3. We got alpha 1, alpha 2 and alpha 3. So when you solve for this, you will get a vector. This is nothing but a W vector because we have used this formula of W, alpha I, Yi, Xi. This is A component, this is a C component, this is a bias component. We can reduce this further by divide by 0.1243 just for a normalization purpose. 243 divided by 0.1243. So if we do this, we will get 1, 1 and minus 10.057. This will become of a W where A component, C component and B component. So bias B is minus 10.057. And now this is what I had explained in the last class, another form of equation where we can get the y-intercept is minus B by C, minus B by C. So when it's minus 10.057 is a y-intercept. And the slope is minus A by C. So it is minus 1. Slope is minus 1. So WB, you can say, if you look at over here, this is slightly about 10 on a scale. This is a y-intercept, which I just calculated in previous slide. Y-intercept is nothing but minus B by C. This is exactly same what we have done in the previous linear SVM class. Minus B by C. Minus which minus 10.057 upon C is 1. Minus minus, which is plus. So you can say the y-intercept is here. It's intersecting the y-axis in somewhere 10.057, and the slope of this line is minus A by C, which is 1. Minus 1. We got exact decision boundary which separate this blue and red set of points. Okay, so that's all.
Ma'am, I have a query.
Huh.
Ma'am, can you go back to the slide where we identified the support vectors? Ma'am, here, like once we got the data transformation for red, so how are we calculating the support vectors? We'll be drawing each and every points and we'll drawing the perpendiculars, and like how will we get that these are the support vectors?
See, this is so here we are not going in that longer method. This is only by visual inspection. We can, from this, you can clearly see S1, S2, S3 are support vectors. Idea is just to understand how the non-linear transformation happens. In original, how can you identify the support vectors? By looking at you have to solve the entire SVM problem, finding out all the alpha values. And whenever the alpha values are non-zero, those are the support vectors. Correct?
Yes.
But that we will not do it. It is very long calculation. So just to understand the end-to-end flow, We are visually identifying the support vectors in this toy example S1, S2. Here you can see S1, S2, S3 are the only border points, right? Visually we can identify the border points. But yes, we can write a program and then you can check the values of alpha. Whenever the alphas are coming non-zero, those are the support vectors.
Got it. But here, in interest of time, we visualizing it.
Yes. We can't do because it's very difficult to solve the entire problem with pen and paper.
Okay.
Here just we are using the same support vector, same three test points, use alpha, calculate the value of alpha, which will give us the W value, and W will give us the slope and intercept of a decision boundary. That way we are solving problem. Okay. Okay, this is some theory you can read on your own. Let me just explain this mathematical comparison of logistic and the SVM. Okay, this equation, does it look familiar? What is this equation? The first J of theta. Is it binary cross entropy? It's a binary cross entropy, and we have a regularization term, L2 regularization. This is the logistic regression cost function, which is a regularized logistic regression. Now support vector, in the support vector, this is the, okay, forget about lambda. Let me just write here. This part, what is this part? I can consider this as a objective function. Okay, let's go. This is a cost of a positive class. This is a cost of a negative class. It's a negative log likelihood. So rather than this, I'm writing cost of a positive class, which is 1. Cost of a negative class is cost of 0. And then I'm getting rid of this m, 1 by m. For a simplicity, we are getting rid of 1 by m. It's a constant. From logistic regression cost function, okay, this is a little difficult. So if you want me to continue, I can explain, or you want me to leave it for a self-explanation?
No, ma'am. Please explain.
Okay. So from a logistic regression, what we are doing, original cross entropy function, we know this first part is nothing but the cost of 0 class, one class, and cost of 0 class. So we have simply written, say this is the cost. In logistic regression, we use the log likelihood or the cross entropy cost function. Now I'm going to the next page. Let's substitute wherever there is C as 1 by lambda. So indirectly lambda is what? 1 by C, or you can say C is 1 by lambda. And rewrite this equation, what was in the previous here. So what I'll do is I'll substitute C here, which is 1 by lambda, and I'll remove the lambda from here. It is 1 by 2. We have got the different version by introducing this C, which is equal to 1 by lambda. Still, it will have a minimization objective. Now, what is this? Can I say it is norm of W square? And this is half.
Ma'am, why is it coming as C and not 1 by C?
Because of this minimization objective, either I'm removing lambda, divide by lambda you do over here, here also divide by lambda. Okay, so this lambda will get cancelled. We will get 1 here. And this 1 by lambda, I'm putting it as a C.
Okay.
Ultimately, it's an entire function of minimization. So for both the term, we are divided by lambda. First term and second term. Now the second term is nothing but what? What is the second term? It is the objective function, right? of SVM. Correct? What is the SVM objective function? W, theta, whatever we can write. So what is a regularization term in logistic regression? That is actually the objective function of SVM. And the first term, what is this first term? After we have simplified y into cost of this, 1 minus y into cost of this. In case of SVM, this cost is nothing but the slack variable. So this is a hinge loss. This entirely is a slack variable. So from mathematically, from the logistic regression, we have come to the cost function of the SVM function, where the regularization term for the logistic regression is actually the objective term for the SVM. In one very shortened notation, say SVM, this is a slack variable. Okay, and this is our objective function, norm of W square by 2. In logistic regression, this become the regularization term. And in SVM, this is the objective function. And here, this is a hinge loss. First term, which is nothing but a slack variable. And here, this is the sigmoid loss. It's a logistic function. It's a cross entropy loss, which uses the logistic function as a hypothesis function. This is you don't need to, if you do not understand this detail of all this diagram, all this detailed function, maybe anytime when you are free after the exam, you can just go through. This is nothing but, it's a hinge loss, and this is nothing but a cross entropy loss. Sometimes this cross entropy loss is also known as a negative of log likelihood. The derivation, we start from a negative of log likelihood and derive to the cross entropy detail expression. So this is a relation between SVM and logistic function. And a very, now you can say loss function of SVM is written in this way, where Z is this theta transpose X into Y, and loss of regularized logistic regression is again written in this way. When we put the SVM loss is a hinge loss, so you can say this is the SVM loss. There is abrupt change at this point, but for a logistic regression, it's a sigmoid function, so it's a S-shaped curve. This is an S-shaped curve, and for this, we get a very sharp change at the point, at this point. This is just a similarity between SVM and logistic regression. Not so important from the exam point of view, but for your understanding. And some reasoning point. And some theory.
Ma'am, this will not come in exam.
Not the derivation kind of stuff. Maybe some reasoning kind of questions you can explain, you can understand, but not to solve any problem or compare or nothing like that. Yeah, and then you can have, because it's anyway open book exam, so if anything comes reasoning based questions, you can open the slide and you can answer it. Yeah, certain again theory part of it. What are the pros? There are a lot of pros of SVM. Due to this kernel based function, we can have any nonlinear function can be approximated with SVM. Then test time, this is a very compact. We only need to store these support vectors for the inference. Generally, when we train the model, we save the model for the inference, for the deployment purpose. Here, we just need to save the support vectors information, coordinates, and those alpha values. So works very well with a small training example. But the problem is how to find the best kernel function. It's a hyperparameter tuning problem. Training time, we have to compute the kernel values of all the examples. So computational and memory requirement is large for the training, and the time also requires more when we have a very large data set. So these are certain pros and cons. That's all. And the summary is just added. Mathematical summary is added for your quick reviewing. That's all. So it seems no question. So it's have you gone through it, or you have to go back and read it? I mean, go through the recording again. Okay, so
Go through
FVM,
the recording, ma'am.
you have to go through the recording. Yes,
Mhm.
that will only it will help you. The last one is remaining fact ML. I'll tell you what is that. Fair, accountable, and transparent machine learning. Very interesting and theoretical. We will just give the introduction. You have one elective in some second or third semester that you can choose. We will talk about bias, fairness, and interpretability. So what is fairness in ML model? Whether is it bias, our ML model is biased towards any gender or towards any ethnicity. So introduce the fairness in the model building. Accountability. When the prediction goes horribly wrong, who takes the responsibilities? Transparency. Whether our ML models, I mean, we develop ML models, some data. So are they comply with any regulations? Privacy issues, how to protect the users, how to protect the data. Security issues, there are a lot of data poisoning attack. Maliciously, the wrong data has been injected into the model. So all are the emerging topic regarding the machine learning domain. So they are the real examples, and a lot of lawsuit can also be, people can challenge certain behavior in the law, in the court of law. And this has actually happened. Say, for example, Amazon secret AI hiring tool. This was internal to AI, but it had come in the news. Penalized resumes with word women's. It's the AI algorithm. Then HP looking into claim, there was some claim webcams can't see black people. Then New Zealand passport robot. So for the immigration check, thinks the Asian men's eyes are closed. So passing through the New Zealand immigration in New Zealand airport. Because you can see this detection of whether eyes closed or open is difficult. So this kind of bias are introduced in the model because of the data. The input data has got the bias in it. Now there's algorithmic bias. There was a case study. You can refer this paper. It's a commercial risk assessment software known as Compass. And it has given some kind of risk. It's a risk assessment for creditors and loan and etc. Which has got 137 feature. It can predict the, for a certain experiment that they have done, it predicts the defendant's risk of committing a felony for a crime. And this is what the conclusion made by this researcher, that it is in favor of a white defendants against the black inmate based on 2 years follow-up study. So what this software is predicting that a person can be felony or not, that a prediction, crime behavior prediction. And then software was actually predicting more black people as the possibility of performing a felony or something like that, some kind of crime. So it's very interesting paper. You can read this study. That's algorithmic bias of this software. It's AI based software. Fairness. So obviously gender, ethnicity, race, color, religion, all should not be, you should not capture your data such that this data, you should not, you should pre-process your data if your data set has captured such information. So that way you can ensure the fairness. Say this example, your data, collected data has got one column, race and ethnicity, Hispanic, white, and so on. This would be learnt by your model. So during data pre-processing, we can create another feature. We can perform some feature transformation and simply create, say, we'll change the feature name, often goes to Mexican markets. So you can say Hispanic is, say, maybe Mexican and white may be American. Rather than differentiating between Hispanic and white, something of this can be created to avoid bias in the data. If the data will have a bias, definitely your model will learn anything coming out of that bias. Another example, long hair, that means women, and short hair, that means men. Another example of bias. You can read this. It's a very stereotypical data set. It's a natural language data set. The physician hired the secretary. Now, by default, because the data we have collected, maybe from all the physicians who are male. So the model learns the relationship between physician and the gender is he, because he was overwhelmed with clients. Second statements hired the secretary, and the secretary, the gender is recognized as she. Say this is kind of some sentence generator app, sentence generator model. So stereotypically, secretary, that means female, physician, that means male. How this kind of bias comes into learned by the model? Because the data, while the collection of a data, some people have not pay attention to that. There has to be very balanced data set. Not only going to the physician who are male, but also collect the data from the physicians who are equally, women as well. Similarly, whose secretaries are also male. So such kind of data collection is very important so that our model doesn't learn this kind of biases. Okay, that was about fairness and bias. Now we have interpretability. How do we interpret the results of the different ML algorithm? Here I will explain 3-4 algorithm, and obviously you can understand in terms of accuracy, but the importance of the weight, interpretability of the weight, and certain other aspects that I'll discuss. So yes, model designers, all, but why we are making certain decision. If as you are ML engineer and you want to say, you want to convince that why you have made this conclusion, or you have come to this interpretation, for that you should be able to explain the ML model's results. Say, let's say linear regression. This is a linear regression equation, right? Where beta 0, beta 1, they are our weights. Simple W transpose X, W's are our weights. These weights are the interpretable components in case of linear regression. So what is interpretability? Suppose our feature is a numerical feature. Say, for example, number of bedrooms or the area in square foot, and we have a housing price prediction problem. If the numerical feature increases by 1 unit, then prediction of that target will increase by your weight units. Similarly, if a categorical feature changes the category, then the output will increase by whatever is the weight, corresponding weight for that feature. So let's take this example. This is a bike rental. No, this example, yeah. It's a data set of bike, rent a bike. Okay, and these are the features. And the target value, how many bikes will be rented on a particular day? That's a target value. So I've given a reference at the end for very detailed understand. It's an online book. You can refer a detailed understanding on this interpretability. So say my target is number of bikes rented on a particular day, and based on, so we are predicting number of bikes. It's a regression problem, and we have all these features: season, spring, summer season, fall season, holiday, it's a working day, weather, misty weather, rainstorm, snow weather, what is the temperature, humidity, wind spin, days since 2011, some random feature. So these are the features, and we have trained the model. After training, these are the weights that we are getting, and we have a bias term of this, and this is the standard error. Say for example, now let's interpret this weight of 110.7, weight of temperature. We have a temperature feature, so you can see this is x0, x1, x2, x3 feature, x4, x5, x6, x7, x8, x9. There are 11 features, and we have temperature W8 into x8, which is nothing but 110.7 into x8. This is a parameter value. This is the weight value that we have learned after training the model. What is interpretation of this weight? If the x8 feature, that is a temperature feature, which is a numeric feature, temperature in Celsius, if the temperature increases by 1 degree, the number of bikes that can be rented, our predictions tells that 110.7 more bikes, or total number of 110.7 bikes will be rented. The temperature increases by 1 degree. That's interpretability. Say, now we have a categorical feature, say for example, weather. Rain, snow and storm. Three, all of them, if there is a rainy day, there is a snowy day, there is a stormy day. Then estimated number of bicycles is, what is its weight value? Minus 1901. So it is minus 1901 lower than when it is raining. I mean, whenever it's raining, the people will take minus 1901.5 number of bikes compared to take a bike when there is a good weather. But if a temperature increases by 1 degree, then the number of bikes that can be that will be rented will also increase by 110 number. By every increase in temperature, 110 more bikes will be rented. This is way we can interpret the weight of every feature in linear regression. Now this is a visual interpretation. Just read this diagram for 2 minutes. Here the weights are represented as the points. And we have on y-axis, we have all of this features. And this is the weight estimate with the points, and we have this 95% confidence interval. So just whether this weight has got any statistical significance or not. So we are also trying to understand the statistical significance of all the weight values. Now say temperature again, because we see temperature as a positive effect. Every increase in temperature, the people who are renting bike keeps on increasing. And I'm the owner or rental agency. We want to keep a stock of the how many bikes we should have on any day. You see, this is a very small number and a very small confidence interval. And it is very close to 0. But from the previous weight estimation, we can see this. It has got a very prominent effect, a very positive effect. Because all of these features are on a different scales. No standardization or normalization has been performed. That's the reason you can see also weight also having a very large range. So that's another reason that you should always perform the normalization and try to bring all the features in a similar scale. But here, this is a case which is not done. Now look at this weight, weather, bad weather. You can say here, the 1900 less number of bikes would be rented with its corresponding confidence interval, plus and minus here and there. Now, okay, look at this season summer. Okay, which has got a positive in the summer season. The number of bikes rented will be say some number. Season summer, what is that? Season summer, yeah, 138.2. So its weight value is 138.2. So what is the interpretation? That for a summer season, 138 more bikes will be rented. That's what our model is learning. But you can see that when we draw its 95% confidence interval, it includes 0. So it's a statistical concept. If our confidence interval includes the 0 value here my value is weight, the weight estimation we are doing, so 0, then this result is not statistically significant. Now you can say that weather season, summer, spring, fall can also be identified by a temperature. Can I say that? By looking at the temperature, whether it's a summer, it's a winter, it's a fall, we can always infer, correct? So this is an example where there's a high correlation between season summer and temperature, season spring and temperature, season fall and temperature. That's why statistically, these results may not be that significant, especially in the summer case, because its 95% confidence interval consists of 0. So even though we get some interpretation, it may not be statistically significant. So likewise, lot of interpretation can be obtained by every algorithm. There's a very a different branch of machine learning. Well, it deals with the interpretability. Now for the decision tree, how will you interpret a decision tree? Decision tree is easy to interpret. Linear regression is easy to interpret. Okay, so we have the same bike rental count. Here, suppose our model learns this as a root days since 2011. And then if number of days since 2011 is less than 434, this is left branch, greater than or equal to 434.5, right branch. Then again left branch, we have some nodes, and then we have left and right branch. And then we have the number of examples that are there in every branch. This is our complete decision tree, which is a depth limited tree. We have pruned the tree. And we can draw this box plot here. So this box plot tells us what is a data distribution. There are 106 points in this branch. What is 10? Now what is it 106? Which tells us how many number of bikes. So you can say this, the rental bike value changes in this range. So the box plot here shows the distribution of a bike count in the terminal node. Out of 329 count, like we have a 329 data point, this is the data distribution, that number of days, number of bikes which have been rented. So this way we understand that in this branch, there are only 70 data points. For each of the data point, say 70 days, for example, then how many number of bikes are rented? So box plot gives us the spread of the data. So that's another way we can introduce interpretability using visualization here in the decision tree. Now KNN. KNN, there are no parameters. So there's no interpretability at the parameter level. But for a low dimensional data, we can interpret a single instance in a data set. Okay, so whatever is the new instance, we can interpret. That's the base of KNN algorithm, that if animal quacks like a duck, walks like a duck, it is probably a duck. So based on that interpretable, whatever are the features of this star, if they're near to the blue data points, those features are equal. So at a very local level, that instance level, we are able to perform the interpretability. And KNN, the base is like that, concept is like that. The neighborhood, look at the neighborhood, and all the neighborhood will exhibit the similar features, similar characteristics. Obviously, that holds true when the number of features are less. If the number of features keeps on increasing, the probability of this holding true is also keeps on decreasing. So there is always an interpretably and performance trade-off. The very simple algorithms like linear regression, you can just see later on, but probably this is not so much visible. As the model is more interpretable, the error rate is high. So this error rate is very high here, y-axis, but these are the model which are more interpretable, like linear regression, decision tree, they are more interpretable. Neural network, on the other end, or the ensemble algorithms, they are less interpretable, but the error rate are low. So interpretability and the performance are always, there are various studies have been done, especially for such a high complex algorithms like ensemble and neural network, how to make them interpretable. So whatever your model is predicting, it has to be based somewhere so that you can communicate this to your conclusion to the higher management. So that interpretable is a whole another branch, which is very interesting to know. Here we are just giving an introduction of how we can interpret the results, weights, etc.
Ma'am, just
Yeah.
one question. So this interpretability we can also achieve by Shapley graphs, right? Shapley values for a
So
model.
there are tools available which can help you in interpretability. Yes. Yes.
Okay.
Yeah. So that's what I said. There are a lot of techniques and tools and the study have been done how to understand this interpretability. Tools are just somebody has done some theoretical analysis and converted into tools, so it's easier for us to use it. Yes. Yeah. So that's all a small understanding of this fact purpose. It's very important to interpret the results, weights, results, etc. Because ultimately you have to make a decision. So for a decision support system, interpretability will play a major role. Okay, so I have completed the syllabus here.
Ma'am, you had told
Huh.
you'll do one numerical on decision tree for logistic regression.
We have done that, right?
No, I think for logistic we haven't done.
No, logistic regression, what numerical? We have already done logistic regression. Or what you're telling, this decision tree? No, you're telling logistic or decision tree?
And you told one example like you'll show towards the end, like last
For?
lecture.
For what?
For decision tree only.
Regression problem.
Yes. Sorry.
But that class I had shown in the class, or no? Somebody had
No,
asked before.
You said you will show decision tree for continuous variable.
Not shown. I didn't show this before.
No, not for classification, but for regression, how we will solve the decision tree.
Okay. Okay, I think I've got that slide. I thought I have showed. Maybe that class we were lagging behind, so I said I'll show at the end. But before that, have you gone through this paper? Yes. This was uploaded. This is uploaded on your Takshila. So any question you want me particularly to discuss this? I'll simply scrolling.
Ma'am, in the question paper pattern, it was mentioned model evaluation and comparison for 4 to 8 marks. This is a general model evaluation and comparison, like they will ask for to calculate values for 1-2 models and then compare the metrics.
Hyperparameter tuning. What is model selection and model evaluation? We use a different evaluation metrics using a different hyperparameter values and find out the which one model is fine, right? That's a model evaluation. Evaluation metrics of regression and classification. For regression, ask for adjusted ask for that we use. Then change the hyperparameter value, you will get a different value. Classification, we have a different classification evaluation metric. And we change the hyperparameter value. So one hyperparameter value, one model, another hyperparameter set, another model. And we evaluate all the models. Then we have a cross validation technique. That's a model evaluation and comparison.
Okay. So I was just thinking in the handout, lecture 5, lecture 15 is having the name of machine learning model evaluation and comparison. So is there anything different?
See, this is how I started comparing ML classifiers. Right? It's evaluation metrics which already done. This is what is mentioned in the last module.
Okay, got it.
Yeah, so I was talking about this question. If you want to just spend 5 minutes, quickly go through the questions which you do not understand, let me know. I will explain. Meanwhile, let me just find out what problem statement you are telling.
Madam, maybe slightly disconnected to this conversation. I know fact is elective next semester. Is it theoretical? Will you be taking it?
No, I'm not taking.
Some...
I don't take factable. No.
Okay.
Yeah, it is. I don't know how it is. I guess it's theoretical or what. I actually don't know what is the handout in that.
I went through it, looked theoretical, but interesting also. So I was just wondering.
It is interesting. Yes, it is interesting.
And ma'am, continuation to that question. So next semester onwards, we have this elective like NLP and deep learning perspective.
Yeah.
So can you throw some light on them? Like, what is each of it? Like, how is it different, and which one is more relative in current, scenario? Like, or which should have more future compared to other, or those kind of things.
Okay, more future. See, this is very we have a NLP domain, we have a deep learn, a vision domain. Okay, if you want to go into the NLP domain, both are equally vision and the text. Basically, it's a textual data, unstructured data we are talking about. So the textual data or the image and the video data. And now some new coming up multi-model data where we talk about text also and video also combined together. So I cannot say that whether NLP is good or deep learning specialization. So you just look at the courses which you can take. There are certain conditions, certain core courses you have to take. If you take an NLP specialization, you can still take courses from the deep learning specialization as well, and the vice versa. And there's something called no specialization also, where you can pick and choose your own courses from any domain. So that way, that bucket you have to identify. What are the rules? What are the buckets you can take? There are some rules. If you take NLP, you have to take core in entire some core courses, some elective courses. You see what are the elective courses and like that. So rather than domain, you can choose what courses are interesting to you, and then take it. Both the domain are equally good. And anyway, you have a core course is deep learning and deep reinforcement learning both. They are core course. So the all fundamental courses are covered. But NLP, NLP course, the natural language processing, is not, I guess, offered as a core course. So either if you are NLP specialization, if you're taking that becomes a compulsory course for you. But if you're taking deep learning specialization, you can still take NLP as an elective. So there's some combination and permutation you have to work around. I think you will get all nice introduction of entire system. But which domain you want to go, you have to decide. Text or vision. Both are equal. And it's always good to have a knowledge of both the domain. But I know in the industry, either there are NLP engineers, either there are vision people. There are certain set who works, certain industry who has got products into the vision and the video. So like that. Or generally somebody wants to work with both text and vision both. Then you can come up with your kind of a la carte. You can create your own specializations. That's called no specialization.
Ma'am,
but for
in
non-IT
second,
background people, yeah,
ma'am,
you can continue.
yes, ma'am. Ma'am, in second semester, which subject are you taking?
Right now, I'm not sure. If I'll take deep learning. I take deep learning, but I'll take next time or not, I'm not sure as of now.
Okay.
Yeah, I take deep learning.
Ma'am, as a non-IT person, non-IT background, will a general course be better, as in without any specialization?
If you do not have any liking towards any text or vision, then you can take a no specialization. But you want in your transcripts to look like deep learn NLP specialization, deep learning specialization like that from the job perspective, then you take like that. Yeah, but non-ITs, Yeah, you will have probably more flexibility in choosing courses, but there are certain dependency also. So if you say you have to take some other course, say conversational AI in third semester, but if you have not taken NLP in second semester, you won't be able to take conversational AI in third semester. So like those dependency also you have to look for.
Okay, ma'am, but will we be taken through some sort of orientation on these
Yeah. I
to
think it will
understand?
happen before because your elective, you will start in, you will have get the orientation.
Okay, ma'am.
Yeah.
Right. Thank you.
Which specialization would be tough in terms of which require lot of maths knowledge and which is more dry? You have any idea?
No, now even you take any specialization, there are a lot of electives. So you can choose electives. There are even, I think, new specialization also coming up, may not be for your batch, maybe new batches. So there is with specialization only 2-3 core courses, fundamental courses, and then there are a lot of electives you can choose from. There are common set of electives also you can pick up. You can pick up the cross specialization elective also and the current specialization, but there are certain requirements. So I don't know, I don't remember those numbers and the exact details. You will get orientation, some document, email, you will get everything. I think maths is, or deep learning will have maths, deep reinforcement learning will have again some maths. That those are two core courses next semester. Nothing much NLP, nothing much 1 or 2, but maths you can't get rid of yet so easily.
Okay.
Yeah. Okay, you wanted something, right? I'm searching where it is. Let me see. I think I also had uploaded. I remember I had explained in boosting, right? There was one boosting problem, and then you were asking regression tree, correct?
Yes, I have asked, but you said just to consider the tree for now, but how the tree came, you will explain it later.
Okay. Now from the past year's paper, are you want me to explain anything? Just spend 5 minutes on that. Okay, that's more important. So you will get an idea.
The slides that you have given to management will have solved examples, ma'am?
Which slides?
That we will get during the exam.
No, those are the slides which are uploaded on Takshila.
Okay, so
see, mine's are same slide. There's examples. There are no differing examples. Maybe some theory, some diagram, or some flow I might have changed in teaching. What I feel appropriate to teach first and then next, like that. But the important points, important concepts, important examples, and the numericals are same. Whatever is uploaded in Takshila. There's nothing extra different than what is uploaded. I'm taking it. Just that how I would like to teach, I have changed a little bit of flow. That's all. And maybe 1 or 2 diagrams, somewhere graphics extra. Sometime if I suddenly get some nice graphic for explanation, I might have added in my slide. So go through the Takshila, whatever is uploaded. And there are student version, there are certain extra available. No. So content, the topic you can take from my slides, and those corresponding topic, what is uploaded on Takshila will be, you will get as the for the reference. What I understand on the Takshila, there are extra student version available for the practice. That practice part won't be available to you. Only the faculty slides would be available. Okay, but the topics what are covered, the problems what are covered on the faculty slides will be available. So you have to do a little bit of matching from my slides and whatever is available on the Takshila. So what I understand, the student version, we upload the 2 different versions, student version, where certain extra topic for a self-study, for extra numerical, for a practice and all is given. But that won't be available, that extra part. So please compare the my slides and compare the topic-wise comparison with the Takshila, whatever is available. And that will be available for you for the reference. And yes, you can take the publisher's book. Yeah.
Ma'am,
Ma'am, you said that you will be explaining the decision stumps, madam. That the question number 4.
4. You want me to explain 4?
Yeah. Is it the yes, ma'am.
There's no explanation given.
Can we take it only the vertical horizontal also? Can we take, madam, here?
You can take horizontal also. That is okay. This is one. Yeah, this is one possibility of vertical. Yeah. So okay, let me just take what you do. How many iteration? Okay, so we have some original data set, something like this. If in the first iteration we take this as a stump, left is plus, right is minus. So all of this, all the 5 data points will be classified as the plus. There are 4 correctly classified points. You can see whose weights are reduced. And we have center misclassified point. Now this is a boosting algorithm. So AdaBoost you assume. AdaBoost algorithm. And the second, this is the first iteration. Second iteration, the more weightage will be given to the misclassified points. So we will come with this decision boundary. Left is plus, right is minus. So in this case, the correctly classified points will be, the weight will be reduced. This is also correctly classified, that weight is reduced. But now we have got a third iteration. We have certain misclassified points. Which are the misclassified points? This too will be misclassified points. So now the attention is given to those 2 misclassified points. So we have coming up with this decision boundary, where the right hand side is plus and the left hand side is minus. So with this, the weight of this will be decreased. Now we will end it here, because in the first iteration we got 4 points correctly classified. In second iteration, the minus, which was not correctly classified, in second and third iteration, the minus point is correctly classified. Say I'll give the number. This is 1, 2, 3, 4, and 5. This is 1, 2, 3, 4, 5. Say 1, 2, I'll give this 3, 4, and 5. 5 data points. Say 1 and 2. They are classified correctly. In how many iterations? Yes.
2 iterations.
1. Even in the second iteration, 1 and 2, right? Iteration number 1 and 2. Okay, then point number 3, classified correctly.
2 iterations.
2 and 3.
Correct.
And then we have classified the points 4 and 5. Classified correctly, which iterations?
1 and 3.
1 and 3. So now you can see this, by combining this, we have AdaBoost algorithm. So the final classification is combining the result of these 3. Okay, so when we combine these 3, all the points, whether we combine the results at the end, all the points will be classified correctly. That's why we will end it at the third iteration. You can take horizontal line also, you can take vertical line also. Even you can always start with like either here also. But then entire orientation will change. With this decision boundary, this is the results that we are getting. But number of iteration will still remain 3. Okay, anything else here? So if you look at the Lagrangian, there's no very complicated calculation, very simple. Calculate the derivative, form the Lagrangian equation, form the KKT conditions, and this is open book exam. So you will get all those KKT condition and like that. So this is easier. Even EM algorithm, you got the equations, and there's a simple data set. So one-dimensional data set. And read the question very carefully, even answer all the explanation also given carefully. Not very complicated or complex calculations are given, time consuming calculations are given. And formula, to anyway, you should know only which formula to look for immediately. So it is done. KNN is straightforward equation. This is information gain. So decision tree based problem. Yeah, seventh one is on MLE. If you look at the solution, it becomes very detailed solution and very standard solution. From the likelihood equation, then from the log likelihood equation, and then we have to estimate the value of theta like this.
But here it's log base e we take for this.
Log to the base.
Yeah.
Yeah. And this is our classification matrix problem, confusion matrix problem. Okay.
Ma'am, so this sample web doesn't contain SVM. So what it can infer, madam?
It doesn't consider SVM. Oh, no, SVM can come. Yeah, no, SVM can come definitely.
Till what depth we can?
We have got SVM. No, why? It is the Lagrangian function where it is used.
Okay. Okay.
Here, where it has gone here, right? Yeah, it is there.
So I'm thinking the SVM with the kernel tricks.
Okay, this is what you can even assume here as well.
And this pre-midterm is 5 to 10 marks.
Yeah.
10 marks will be like almost 1/4.
25%. Yeah, generally could be 70-30 ratio, right? The 70-30 ratio, 80-20 ratio.
So ma'am, for pre-midterm, which is the important topic?
That I cannot say important topic as of now. Linear regression, logistic regression, those are the important algorithm. Decision tree. Here the decision tree is used, right? In the pre-mid semester. Yeah, it could be decision tree. Any of the algorithm can be chosen. How many you have done?
Confusion matrix is
also used here, right? KNN was here.
Yeah.
KNN is
So
post,
KNN was not part of pre-exam.
KNN was
Acha,
confusion matrix was.
Confusion matrix we covered in pre-mid semester. Yeah, it could be like that. You cover everything. Linear regression, logistic regression, then what we have decision tree, then what we have done pre-mid semester, which other algorithm, one more we have done. Or only this much. Decision tree, logistic, linear. There are three major algorithm, yeah. And all the
and linear.
and evaluation metrics in detail for both regression and classification problems. Yeah, the major topics you have to consider. All of this we have
done. Is major, ma'am.
Yeah. Yeah, tell me.
This paper has 8 questions and need to be solved in 2 hours. Is that possible?
2.5 hours. 2.5 hours. 40 marks exams are 2.5 hours. 30 marks exam for 2 hours. No, this is not 2. This has to be 2.5 hours. Huh? There's a mistake.
Okay, so our exams are also of 2.5.
You have been given timetable. No, check in that. What is exam timetable? I think
I saw it was 3 hours.
So no, 2.5 hours. After that, you will get a time for scan and upload, 15 minutes. You cannot write during that scan and upload. You know the mid-semester rules. Same applies here. So 2.5 hours for exam and 15 minutes for scan and upload. It is 2.5 hours exams.
Yeah, 2.5 hours.
Okay.
Ma'am, the lab part, can we access them even after the semester?
What part?
ML lab programs and all. Are we be able to access?
Which some lab where you got access?
Lab notes we were given with zip files, right?
I don't know which zip files you're talking about. See, one is demo, what I am uploading on Microsoft Team, which you can download it. Something which is available on Takshila, which you can download. Now, something you're talking about Novepro Lab, Virtual Lab Excel.
No, ma'am. For ML programming lab itself, they have given us few zip files where.
So where is the lab? Physical. What lab you're talking about? Which platform the lab was hosted? That's what. Is
In
it
the
a virtual lab?
Takshila, ma'am.
You're talking about data sets actually.
You download it. I don't know. You will get, yeah, the access will be there till you complete your MTech, I guess. Otherwise, if something is downloadable, you download after the exam.
I think, madam, those data sets are publicly available. Kaggle, everywhere we can get.
That is there, but whatever is available on Takshila and Microsoft Team, after exam, you can download it. You will anyway need for exams also. That access will definitely stay, but I don't know how long it will stay. Like after your MTech is over, I don't know. So after you can download everything. This is a regression tree. I have already updated, uploaded along with boosting PPT. Okay. Have you gone through, anyone gone through this? I remember I had explained, but okay. The steps are also mentioned. And I've given this reference where this entire example is taken. So how does, like here, we don't calculate the entropy or the information gain, but still we have to calculate the impurity. There has to be the impurity reduction when we keep on drawing the different nodes of the decision tree. So we start with the all training examples and the root node. For each feature in the data set first, sort the values in the ascending order. Then consider all the midpoints between adjacent value as a potential split points. So say I have this many features here. See, this is not important from the exam point of view. You really want me to explain this right now? No. It will take some 15 minutes also.
No, madam, it will confuse
No, ma'am.
our. We have already ordered.
Upload these slides, ma'am.
It's already uploaded. No, already there. So it's session.
Checked. In boosting, these slides are not there.
No, 1 minute. Let me check.
Ma'am, in Takshila or in Teams?
Team. I am uploading everything in Teams.
Teams, okay.
Yours is section 6, right? Or section 1?
Section 6, ma'am.
This is a class, right? So files. Here. Boosting. Download it better. You just download it. It is available. Okay, let me verify. This is the same thing. How do I download?
From those 3 dots.
No, but that's not coming. Here.
Yeah, see
okay.
here it's coming. Yeah.
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 Oh, it is not uploaded. I'll upload this slide. I think this is what I downloaded. Let me delete this from here. Okay, I'll upload it.
One question. When can we expect the semester 2 to start?
24th May.
24th May. Okay.
Yes.
And those electives has to be made in between that.
Yeah, so some orientation will be done. Now I have uploaded. Just check whether the correct version is being uploaded or not. Please check. And the other two also I'm uploading, SVM2. And this FactML. Okay, now everything is uploaded. Please check once.
Miss, the one that we did today after SPM, is that important enough for the exam?
What after SVM FactML?
Yes, yes.
Yeah, interpretability. It's not difficult one. No, that's why I covered today. It's can consider. Some maybe.
The exam, are we expected to have any questions on that?
Maybe 2 marks, though, although it's not mentioned in the pattern, maybe some 2 or marks question. Pattern it's not mentioned, right? Here.
Yeah.
Yeah. Then don't assume, but yeah, anyway, it's covered and it's also open book exam. So even if comes, it should not be difficult.
Ma'am, where is this QP pattern uploaded? Like I can't see that.
Takshila must be. You can ask your.
It's in Takshila, okay?
Okay. Any other doubts you have? Boosting is the correct version is uploaded. Can you please confirm? Are you checking? Somebody checking? Please, somebody please check that boosting or I've uploaded some different version.
Yes, ma'am, check.